This is the final chapter for exam 3, chapter 8. And this is on rotational motion. Okay. So, I'll go through this. Then I'll have the review for exam 3, which opens on October 24th, for which will be on chapters 6, 7, and 8. All right. Okay, so rotational. So we talk about linear motion. All right. Moving a straight line, right? X, and we have V and acceleration and the relationships between those. All right. And then we've talked about, and then force is mass times acceleration. In linear, so we're talking about in a straight line. And this could be either sideways or up and down. Again, when we have vertical, we have gravity involved. All right, and then when we have rotation in the sense of something moving at a constant speed of radius r, then the centripetal acceleration is v squared over r, which we've seen before, right? Well, that's the speed, meters per second, that's the radius. All right, all of this is still there. So we have a constant velocity here, all right? V is constant. All right, now we're going to get into what we call rotational motion. And in this case, we have like a thing rotating, and like it could be a merry-go-round or something like that. And we define a rotation. All right, when we go up or down, we call up as positive, down as negative. We rotate about a center. I mean, we can rotate either direction, counterclockwise or clockwise. So for definitions here, we define rotation this way as positive and this direction is negative, all right? Because it makes a difference how you're rotating, whether they're that way or not. All right, so what we're going to introduce here are concepts of rotation, and the way this works is, again, when you move on a sphere, on a circle, right, you go, the circumference, C, is 2 pi r, right? So the different distance around is 2 pi r. And what we define is a distance, if we're moving a distance L on here, on this ring, we define an angle theta, and the angle theta is given by how far we've moved along the distance going counterclockwise from the x-axis divided by r, and this is in units of radians. And basically it's how many radius you're going. So if you go 1 radian, so this is distance r, if you go 1 radian, that would be a distance r equal to L. 2 radians would be that far, 3, 4, 5. And so in a circumference, the circle has a circumference in terms of radians is 2 pi radians. So it's not an actual measurement, but it's how far in terms of angle. And we know angles, we have angles, so if you measure in degrees, a circle has 360 degrees, which is equal to 2 pi radian. And it turns out, if we go an angle of corresponding, so this distance L equals the radius, then 1 radian, RAD, is approximately 57 degrees. All right, so we do it in terms of radians. So it's all radians. It's not an actual distance, but it's in terms of how far angle-wise. Now, one thing about this, like we have here, I'll mark these a different pen. If we have, say, a point A here and a point B here, which is halfway, right? This angle for B, theta B, equals the same angle theta A. Any point along here moves the same angle. But as far as the distance is concerned, say this is 1 meter, and the whole R is 2 meters, so R is 2 meters, then LA, LB, if you go 1 radian, will be 1 meter, LA will be 2 meters, because you're actually traveling 2 meters. The farther out you are, the farther you're traveling. Right, so the actual distance you travel, the farther out you are, will be more. Right, so angular velocity, angular distance is the same. The linear distance is going to be greater. All right, so those are the concepts that we're introducing. All right, next thing we're going to do, this is all part of the book, is we'll introduce the concept of angular velocity, angular acceleration, much like of x, b, and a, and we'll go from there. So, move out a little bit. Draw a circle again. All right. And here's R. That's the wrong pen because it doesn't work. It. Move a distance theta. All right. Again, relationship between, and this is L. Theta is L over R. Now we're going to introduce omega, which is going to be how fast it's moving over R. So how fast you're actually moving divided by R is the angular velocity, and this is in radians per second, right? And then if this is actually, now if it's moving at constant speed, all right, then B is constant. But if it's accelerating, if the outer ring is actually accelerating, so it's going faster and faster and faster, we introduce this concept of angular acceleration, which is A over R, and this is in radians per second squared. All right, so this is a relationship between all of them. All of them are basically the same kind of formula, except we have, instead of x, b, and r, or L, b, and r, A, we have theta, omega, and alpha. So let's call it angular acceleration. Again, reminding you, centripetal acceleration is v squared over r, but v is constant in this case. If we now express this in terms of omega, v is omega times r, so centripetal acceleration is going to be omega r squared over r, which is omega squared times r. So the centripetal acceleration depends on the angular, so anywhere on here, the angular velocity is the same, but it's proportional to how far you are from the center, which makes sense. I mean, the farther you are away, the more centripetal force you're going to feel. If you're at the center, you're not going to feel anything at all. So this is another expression for centripetal acceleration if we're given it in terms of omega squared r. Right? And that's how those things work. Okay? So related to this then, omega, again, is radians per second. The relationship between frequency and omega is given by omega over 2 pi is the frequency. This is in cycles per second or hertz. And again, the relationship between frequency period is 1 over the frequency, which would be 2 pi over omega. Okay? So really it's not a whole lot different from what we've done before, except now we have angular velocities as far as that. And again, anywhere on here, the angular, wherever you are, whether you're point B here or point A here, the angular velocity is always the same. It's just the actual linear velocity will be different because in this case, L will be theta times R, right? Here, V will be omega times R. So again, farther out you are, the faster you're actually going. And acceleration is alpha times R. Notice how all of them are proportional to how far out you are, linearly. Okay. All right. So, not going to get into much of the details here, but if we look at the rotational aspects of it, if we go back to chapter 2, our expressions for linear acceleration, linear velocity, and time. Notice on the right side, we have the expressions that have been used a lot. On the left are in terms of angular motion, and they're exactly the same term, except we replace x with theta, v with omega, and a with alpha. So they're exactly the same kind of concepts, except that's how we're doing it in that regards. Okay. All right. Yeah, that'll work. All right. So those are the concepts there. All right, same as before. Now you can look at the problems as far as those examples are concerned, but this is what we have here. Okay. All right. All right, let's introduce a new thing now, and this is the concept of torque, right? And we use the letter tau here, and the units are going to be Newton meters. Now torque, let's say, you got a bolt, and you get a wrench, and, and you're trying to loosen a nut, and you have a wrench. If you have the hold the wrench right next to the bolt, you're not going to get much, so-called torque on it, because as you have any experience, you can't really twist it much. If you just try to grab it, you can't do that either. But if you hold it farther out and apply the same force, you're going to have that force times how far you are away, and that's what we mean by torque. It's the force applied times how far you are from the center. So it's a very useful, we're all familiar with it, it's just hard to quantify. We have a torque wrench. So what it means is if I have applying about this center, I'm trying to loosen something, I apply a force of some newtons and a distance r. The torque, tau, is force times that distance away from there, right? Now, again, this looks very similar to when we have force times distance, but in this case, F is perpendicular to R. So this is not the same kind of concept we have for kinetic energy of work done, which is force applied in the same direction. All right, go back to there. You apply a force in a certain direction, that does work on it. This is rotation. So we have the same sort of terms, numbers involved, but these are always perpendicular. So they're perpendicular to the maximum. If we pull it straight out, it's not going to do anything at all. I have to push it, and the force is strongest when it's perpendicular to there. And these are units of torque. And notice this is somewhat familiar to Newton's second law, force is mass times acceleration. And we'll get into this a little bit. So what we're going to have here is this concept of, so linear, we have this concept here, force is mass times acceleration. It's all in the same direction. Apply a force, then it will, this is some mass, it will accelerate by this relationship. What we're going to have here for rotation is, we have a concept of angular, so if it rotates, and I'm going to just do it this way, right? It rotates, you put a force on it, and assuming there's no resistance, it will accelerate faster and faster and faster as we go around. So again, our relationship between alpha and actual like how far it's actually accelerating this way is alpha over r. A over r is alpha. And for rotation, we're going to have this torque, and this will be given by, now it's similar, so we get F is, but rotation, we introduce a new concept, I, so we have alpha, which is angular acceleration, and this I is moment of inertia. Okay? And moment of inertia is how something, rotation, in an angular direction. So take this disk, right? It has a certain mass, has a certain radius, certain shape to it. It has a, if I push it, it has a certain mass. Say this tape has the same mass. They both have the same inertia. We both have the same mass. If you want to, you can look at there's a video on the Chapter 8 link of a YouTube video comparing a disc and a ring and how they move. Because what we're going to see, even though they have the same mass, because they're a different shape, they're going to have what we call a different moment of inertia. And this moment of inertia depends on how spread out the mass is, and it's basically given by the expression mr squared. So it's how far out the weight is distributed, right? So in this case, all the weight is distributed around a distance r. For a disk, it's spread out. And what does that mean then? That means it's easier to turn this than it is to turn it, because you have more weight concentrated on the outside. And again, you look at the video that I have there of showing a disc and a ring going down a ramp type. If I drop these, we know from before, they'll both land at the same time because they both have the same mass. Gravity acts on, say, even if they have different mass, they're both going to land at the same time. But rotation depends on the shape. And we have this moment of inertia involved. And the way this works is, I will go through it. There's a table in the text showing the moment of inertia for different objects, all right? As far as how they rotate. So the moment of inertia depends on there. And you can look it up in the text, but I'm going to go through one example here as far as this is concerned. Okay? So, these look very similar, but instead of F, we have torque, and instead of mass, we have moment of inertia, and instead of alpha, we have A, we have alpha. So let me do a couple examples here. Ones we're just going to compare. So, moment of inertia depends roughly at mr squared, but it's a little more complicated than that. If we have a ring like this, where all the weight's concentrated on the outside, right, then I is given by mr squared. So let's do an example here of all right, so I got this ring. I went and found a ring. So this ring has a radius, well, it has a diameter of 16 centimeters. So diameter is 0.16 meters. Radius is 0.08 meters. All right, and this thing weighs about, has a mass of about 2 kilograms. All right, this disc has the same radius. All right, and we have this sphere. All right, this weighs about 2 kilograms too, even though it's kind of small, they both weigh the same. So for a ring, this is, so let's R is 0.08. M is 2 kilograms. For a ring, 1/2 mr squared. For a disc, I is 1/2 mr squared. All right, because the weight is more distributed. And then for a solid sphere, all right, so for disc, as for a sphere, I is 2/5 mr squared. All right. So if we compare these two, because they both have the same radius, all right, for the ring, that would be 2 times 0.08 squared, which would be let's see, 64,000, 2 times 0.0064, that would be 0.0128, right? All right, kilograms meters squared. And for the disc, it'd be 1/2 2 times 0.08 squared, and that would be 0.0064. So it's 1/2. Even though they have both the same mass, they both have 2 kilograms, this would be 1/2. And the sphere is 2/5. So now if you look at the video, you'll be able to see, comparing, again, the video on the link on chapter 8, which one would roll down an incline faster. So an incline would be if I have them both on a ramp, and I'm not going to do here, they do a better job than me. Let them go, which one goes down the fastest, all right? You can see it has to do with the value for the moment of inertia. You can figure that out. And then lastly, considering this is basically one half, 2/5, all right, comparing that, now the video doesn't get into that, but if you were to do all three, you could probably figure out of the three, what would be the order coming down first, second, and third. So this is all related to concept moment of inertia. So they all have the same mass, but because of the shape, the rotational force will be different for each of these. So look that up, look at the video, and compare there. All right? Now, okay. Now I'll get into one last thing here. So this is comparing. These are only three we're going to compare. There's other different shapes you can have, but we're not going to do that. All right. So those are the three: ring, disc, and sphere. Then we're going to get into one last thing here is rotational kinetic energy. All right, remember kinetic energy is given by 1/2 mv squared. If we have rotation, then it's given by 1/2 I omega squared. Notice that instead of m we have I, and instead of v we have omega. So same kind of concept. So something rotating like a disk has a lot of kinetic energy into it, right? Takes a bit of effort to slow it down, a lot of force, torque in this case, to slow it down from rotating, right? So that's the concept there as far as that's concerned, all right? And you can also look in chapter 8.7. It gets into, if you were to compare different objects, which one would land first, which one would be slowest going down the ramp. Right? You can look that up. Now the last thing is concept of conservation of momentum. Conservation of angular momentum. All right. Now in linear momentum, we have linear momentum from collisions from chapter 7. Momentum is given by mass times velocity. And in collisions, momentum before equals the momentum afterwards. And when we have two objects collide, the momentum before and afterwards is the same. Now we can do this same thing with conservation of angular momentum, but with just one object. And the concept here, I'll just bring it up to show you, is the picture again, and if you've seen it, of figure skater. All right, when she has her arms out, she has her arms out, she'll rotate relatively slowly, but then when she pulls them in, she's actually changing her moment of inertia because her weight is now distributed more towards the center, and she will go faster as a result. You've seen it where they go when they hold their hands up and they spin very, very fast. So they have hands out, pull them in, they can go very, very quickly. So this is a concept of conservation by changing it. And we call it before omega 1, I omega, and this will equal to the same afterwards. right? So by changing this, so if I1 is greater than I2, so that when she pulls them in, then omega 2 will be greater than omega 1. So because she pulls it in, makes her moment of inertia smaller, mass is the same, but she'll spin much, much faster. And that's the concept there as far as that's concerned. Okay? There's other objects here. You know, I mean, and you can get into examples of that. But one good example is in astronomy. And the same concept. All right, the sun, which has a diameter, a diameter of, what is it? 1 million kilometers, more or less. Let's do that. Takes 25 days to rotate. All right, the sun, takes 25 days. We can look at the sunspots. It takes 25 days to rotate on its own axis. All right? Now, in 1967, Jocelyn Bell, who didn't win a Nobel Prize for this, discovered this concept of pulsars. All right? And what she found was, by looking at a signal put out in space, what we call radio signal, this thing was going on and off 33 times a second. Okay? 33 times, flashing on and off 33 times with extreme precision. Now, first they thought this was, had no idea, and they thought at first they might be a intelligent forced unit, so they called this LGM after Little Green Men. But then what they really finally realized was this is actually a very, very small object that was rotating, and this is not part of, that's astrophysics. But what it turns out is rotating, it puts out this intense beam of radio waves out. And if you happen to be pointing in the direction, like a lighthouse, pointing in the direction that it is turning, then you can see it flash on. Much like a lighthouse rotating, you see it flash on and off. Now, it doesn't go 33 times a second. Lighthouse goes. But for this to go 33 times a second, what this turned out to be was what they call a neutron star. Again, this is the last aspect. When a large star dies, it blows off, explodes, dies. What's left is only has a diameter of about, say, 2 kilometers in size. So it's very, very small. I mean, it's not the size of Lake Bemidji. So what you have is, instead of 25 days, it rotates at, it's that much smaller. So what we're going to have then is the moment of inertia. Again, moment of inertia, mr squared. So if this thing, from being extremely large, is now compressed to a very small object, it's going to rotate much, 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 much faster. And what this actually is, instead of taking 25 days like the sun, it's rotating 33 times a second, or about once every 3/100ths of a second. So it's rotating extremely fast. This is what we call pulsar. So this is an extreme concept taken from astronomy. Take a big object, compress it down to a very small object, it's going to rotate much, much faster. we see the same concept one last time of comets. All right, a comet orbiting the sun has a very elliptical orbit. And because of conservation momentum, the R here is very small, but the R way out here is fast. So the speed here is slow, but then when it goes around the sun, it goes very quickly. So a fast, slow down. So long period comets, say like Halley's Comet, which goes out to Uranus, spends most of its time way out here around the orbit of Uranus, but then when it comes in every 76 years, comes around very quickly, only spends a few weeks and zooms back out again. So it goes this. And so these are the concepts of chapter 8 as far as conservation of angular momentum is concerned. All right, so that's chapter 8 as far as that is concerned. I'll look at that and have a good day.